Hello, I'm Kris, and welcome to Runtime Optimizations for Compile Time Reflection, a talk where we will use a few of superpowers of C++, not including safety. And the two which we are going to look at specifically is the compile time manipulation, as well as low-level control of the hardware, which can be leveraged by C++. So hopefully that sounds exciting to you. And without further ado, let's begin. So firstly, we'll take a look into the reflection based on the proposal, which is coming to C++ 26. We'll take a look into the introspection part of it, as well as the metaprogramming, which is kind of changing quite a bit into the template metaprogramming space. So if you're excited about templates, this talk will potentially change your mind. Further, because why are we doing that? All of that we are going to be doing in order to boost the performance, because who cares about the performance? Everyone. That's C++. That's the audience. Clap for you guys and girls. So why are we going to look at the performance? Because the reflection part also has the runtime parts of it. One of those meta functions and functions is enum to string and string to enum. Hopefully we'll get to both of them. But why they are important? Because they're applicable in kind of everywhere. So, it's like ID to ID mapping. And that's very common in the hash tables and other things. So performance of that is really critical for a lot of software. A bit of disclaimer, because this talk is heavily proposal-based, meaning I can't guarantee the syntax, although at this specific time of the talk, all the examples compiles on Godbolt. Since there's a performance talk, we'll focus on x86, because there'll be a lot of assembly, sorry about that. And we'll leverage Clang P2996 compiler, which implements the reflection. Thanks, Daniel, for that. As I pointed out, all the examples have the links, so you can always check them out. But I didn't want it to be just hypothetical talk. If I get reflection in C++ 26, maybe I'll be able to do it. All these examples as well are possible in C++ 20. And if you're interested in that, grab me afterwards. The library is provided, which leverage all of that. Okay, so hopefully that sounds exciting, but not as exciting as reflection. Who is excited about reflection? For the recording, everyone basically is excited about it. I am as well. Couldn't be excited about C++ as much for a while. So I love it. So why? Because it's static, meaning it's at compile time. And that's, in my opinion, one of the best choices C++ could make. We know the track record about the defaults in C++. This one is a good one, in my opinion, but time will show. Because we can always leverage compile time reflection into runtime one, but we cannot do the opposite. It's also value and const eval based. As I pointed out, template metaprogramming is not part of it, which changes the landscape quite a bit, and we'll take a look into that. And the reflection has two parts. Mainly, it supports introspection, which is the reflecting enum names or the members tract names and stuff like that. It has the metaprogramming part, which we'll take a look into quite deeply. What is actually interesting, if you look into the proposal, is that it supports stateful metaprogramming, which is in C++ so far kind of a gray area. In C++ 26, if the proposal will go through and it's close to B, you'll be able to do compile time counters and stuff like that using stateful metaprogramming. Additionally, it supports data member injection, but we won't be digging into that. So if you're interested in that, you can take a look afterwards. So how is that looking? The first thing, the proposal is introducing the std meta namespace, where the reflection lives. And then there's like this info object. I'm not going to put the definition of it because I don't want to confuse you yet. But you can imagine that it's type erased, and that's really important because it's not strongly typed, AST node into the compiler. And I think that definition is good enough for the time being. And then we have a lot of meta functions. And when I'm saying a lot, to query this info object for something. And what we are going to leverage here is, for example, enumerators of, which will return a vector of these info objects, which you can query more information about. The other one is the name of, which, as the name says, returns the string view of the info object. So far, so good. I didn't lose you yet, because it will get harder. Okay, so besides that, the metaprogramming part is where the fun begins with P2996. So Reflection introduced two operators. One of them is this caret, may change in the future, but we'll see, which is kind of a lift, like RefFull expert in the previous proposals. And the idea is that we can lift a type on an object namespace into this reflection mode. So if you do the type ID of that lifted thing, it will be the info object in the reflection. Make sense so far? So we get anything, we lift it to the reflection world, where we can do a lot of queries and the meta functions to do that. And then, even more controversial syntax for the operator, it's called a splicer, which is this index, square bracket, colon, and that's kind of like unreflex. So we are in this reflection world, and then we want to go back to source code to our real world, in a sense. So if you take a look into that example here, we lift the int on the bottom to reflection, and after that we splice it with the type name, which give us the type int. So basically that's a full round from int to an int through the reflection mode. So hopefully that makes sense. So why that's important? This type erased thing is important because that allows us to have the common type for the reflection. It's not strongly typed, which has drawbacks. We cannot do overloads and stuff like that, but it allows us to do the following. So imagine that we have the meta function add, which just gets the periodic templates and tries to return and returns the nth out of the pack. So in C++, below 26 or 20, it's kind of difficult to do it. You have to do recursive solutions, many other options. I actually give a talk about it. It's kind of interesting space. But in C++ 26, we will be able to do the following. We can do the array of lift ts as ellipsis, which will return as the array of the info object. So that's the common type, because it's an array. And we just get the n out of it. So that returns the nth info object. And what we do after that? We just splice it back with the type name splicer to the source code. And that will give us just the type out of it. Make sense? Much simpler than compile time magic with the templates. Therefore, the templates are kind of crossed here. By the way, in C++ 26, there is also generalized pack declaration and usage proposal, which has been accepted, and you can do the slicing. We can do indexing. You cannot do the slicing. This proposal has been based on Circle, where you can do slicing as well, like in Python. But in C++ 26, you can do that syntax as well. So you can do more as well. Let's say we want to manipulate these meta functions a bit more. So we get this reflection, and we want to reverse drop or something like that. What is really cool about it is that we can start as before. We lift TSS ellipsis to our array, and we just pipe it to actually ranges, because all of that is consexpr. So we can reverse, we can drop, and we can put it back to a vector. Like, who can understand that code? Like, everyone, right? It's very simple and very intuitive. What we have to do afterwards, there's a meta function for that as well, which is called a substitute. And in that case, we have this vector of info objects, and we can put it back into the type list, which is defined on the top. So we'll go back from the vector to the variadic templates out of that. And that will be still an info object, which we can then splice back to the source code. The substitute is a bit, more tricky to understand, but the idea is very simple. We have the array or a vector of info objects. We do manipulate the way we want it. We can change it. We can do quite a bit of things. And then we splice it back to the world which we usually exist. Make sense? I don't lose you yet? Okay. So you may think about how does it compile? Is it fast? Is it slow? It's, meta-programming. We care about the 10 minutes which we have to spend either way. So it's not great at the moment. I'm not going to lie, but it's improving. So here, the blue line is the ranges, and you can do that with or without ranges. But if you compare that to MP11, it's much slower at the moment. But it's early days, so that will likely improve. But if you're interested in that meta-programming model, you can actually do that in C++17 in all compilers. And if you're interested, you can take a look. So this exact model with ranges and everything, you can do in C++17 too.
Excuse me. Can you explain what the other lines are? Because I can't read through them.
Okay, the question is what the other lines are. So there is, the blue one is P2996, which is the reflection. The second one, below it, is MP11. And after that is P1858, which is the indexing into which is proposed and accepted in C++26. So MP11 basically is as fast as the proposed thing for the C++26, and P9 reflection is not as far. Okay, so we'll leverage that knowledge right now in order to get the performance out of it. So hopefully that will be exciting. In order to do that, we'll use this LLVM machine code analyzer. Anyone familiar with that tool? Not a lot of hands, so maybe it would be interesting. So this is a static analyzer tool. It's available in Compile Explorer, where you can get a lot of information about your assembly. You just give it Intel assembly, and it will produce you, the latencies, throughput of the instructions, as well as timeline, how the pipelining works. You can find the bottlenecks of your registers and resources pressures. So there's a lot of things. And, this is performance talk right now, but I will just scratch the surface. There's a lot of things that you can dig in afterwards if you're excited. Also, perf tools, just to get the benchmarks as well, has been shown many times. We'll get the counters out of it. And there's obviously many tools to do the performance. I've chosen these ones in order to keep it in the scope of this talk. So just to hook you a bit more, because I don't want you to get asleep, and we'll look into benchmarks a bit later, but I'll let you sing that one. So like P2996, which is the reflection proposal, doesn't have the library part to it. It's just the meta functions and the operators. So there is no library yet. It will be later. But you can see here, and there are many different things and solutions. Anyone know Frozen for the perfect caching? Okay, we'll discuss that later. But everyone knows if-else, switch case, I bet, or unordered mapped. So our goal in this talk will be to go from the top to the bottom, and so smaller is better, just to clarify that we're not going the other way. So hopefully that will hook you, and we'll get there at some point, hopefully. So I bet everyone knows what the enum is, but if you're interested, you can read about it in the standard. It's a lot of actually interesting cases for enum. But just quickly, the unscoped enums from C, everyone kind of used them. C++11 introduced the scoped enums, where we have the class, and we can put the underlying type. Another standard term but sometimes used. I've seen that in the field a lot of times. The flag enums, where you set 1 bit per case, and then you can do the pipe out of them. And this one with this operator here, that just multiplication, power of 2, if you're not familiar with the syntax. So, I started looking at it because I seen these examples in P2996, and I was thinking how hard it can be to do enum to string. Well, the first case I thought of when looking at the standard is that you can have the same values for different cases. So if you want to print A or B, what do you print? Well, I don't know. And in this talk, we won't discuss that because we care about the performance, and we'll just take the first one or the last one. But if you really want to have something which works under the hood very deeply the way you want it, that's something to consider. Flag enum as well is an interesting case because if we pipe, we get A and B. So if you want to print, we should kind of print A, B, A, comma, B, something like that. Hard to say. And the last case, when we have something which is not specified as a case in the enum, should we return an optional? Should we throw? Should we put something else empty? And empty is something which we assume because of the performance. So, okay. So with that knowledge, we know what the enum is. We know the reflection proposal. Let's take a look how to implement that in that proposal, as well as the other proposals which are kind of required for this one, which has been the expansion statement. So that's the template for, which have been tried to be pushed to the standard for a while, but maybe it will come. So the way we do it, we do this template for, which we'll explain in a second, out of these enumerators, this meta function, out of lifted E, which is the enum, and we just compare the spliced value. If the value matches, we return the name of for that given case. Make sense? Kind of simple, right? This template for is a bit questionable here because we can simplify that, but overall, kind of simple. So if we take a look under the hood, what that will generate in the compiler, that will be like if, color red, return red, blue, and otherwise just return empty case. Makes sense, right? So that's what we generate out of that code. And notice here, and that was the template for kind of issue, that we cannot break. Although it's a template for, it's for in the name, and for the, out of the loop you can break. Template for you cannot break because this code break doesn't make sense, right? Because it's just substitution of if-else's in that case. So I looked at it and decided to simplify it because we can. And reflection doesn't provide that, but we can do that. So let's take a look into the enumerators. A thing which will make our life easier. We do the index sequence out of all the enumerators, and we'll just produce the array of pairs of the enumerated value and the name of string view representation of the name. So how that will look like is something like that. And the reason we're doing that is just to simplify the execution of the code, which I'll show in a second. But does it make sense? What is that doing? Because we'll be leveraging that quite a bit. So with that in mind, we can simplify our enum to string with the following concept, text. So we have enumerators that returns our array of pairs. We the structure binding, and we just do if, and we're done. So that looks better, right? It's kind of simpler. There's no template for, no cons expr magic, but it has other limitations. We cannot do if cons expr in that case because we have enumeration at runtime. So let's take a look into the performance part of it. So as I pointed out, we'll use MCA, machine code analyzer. So not to give you too much a headache, we'll just focus on a few parts of it. There's much more to it. The latency, which is how long does it take for the instruction to be executed in cycles to get the result. Throughput, how often we can issue the instruction per cycle, and whether we load, meaning we have to access the memory or not. Others, like micro-operation and my store has side effects, we'll just skip for the simplicity. But does it make sense? Everyone understand the latency and throughput? There's obviously the difference. And as you know, assembly instructions are not equal. Some of them are more expensive than others. Some of them are easier to pipeline. Out-of-order execution will be related to the macro operations. But just to get through this example with the if-else, we'll just simply take a look into, it's not really exciting assembly. Why? Because it's just comparisons, right? If-else, 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 and that's what will be generated under the hood. What's important here is that the instructions are simple, so the latency of each of them is 1, and they kind of well pipelined. But it also shows that the performance is not a number, it's a shape. Why? Because here we can have a lot of branch mispredictions, and a lot of, result will depend on the input data and the case which we have. Were we lucky with the branch predictor or not, depending on our input. The further we have to go and the more branch misses we'll have, the lower the performance. So that's something we'll see afterwards. So if you want performance, we have to do a bit more, right? That's kind of silly example, works for up to 5 cases. Otherwise, it's getting really slow. So if you know our hardware, and we assumed here x86, we can do SIMD, so vectorization. Who is familiar with SIMD? Everyone, so yeah. I don't have to explain that. So we have a scalar mode, which we looked with the if-else, and there is a SIMD mode where you have a vector. So the idea for those who never used that is that you can do multiple operations with you can apply operations with multiple data on a single instruction. And there's a proposal for that, which is long time in making, but maybe it will be in C++26, P1928, which is std-simd, and we will just take a look into how this look like. Just about x86, so that we have the common background here. There are different instructions. There's SSE, AVX, AVX2, AVX512, and they differ in capabilities. Most common laptops will have, or common architectures will have AVX of some sort these days, but you can use any of those on your hardware. And the difference will be how many comparisons in that case we'll be able to do. If you have SSE, we can do 4 U32s. If you have AVX, that will be 8. And if you have AVX512, that will be 16. Or depending on your type, you can do more or less. Makes sense, right? Everyone familiar with SIMD. So our enum to string will make just we'll make this optimization only for the case where the native SIMD size will actually fit our enum cases. So if you have, for example, AVX512, we can do 8 ints if that's the underlying type. And if that's the case for the how many cases we have in the enum, we'll just leverage that directly. And what is important here that when we have the SIMD, we have to separate keys and values because we need the contiguous memory in order to do the broadcasting and comparison. But with the SIMD, and there are many libraries, or you can use intrinsics to do that. It's kind of simple. We do the SIMD. In that case, it's native SIMD, but there's like fixed SIMD and just SIMD. We broadcast the value, which is the value which is coming out of the outside, so that we have the vector populated with this value. Then the other, right-hand side will be populated with the keys, which we populated at construction time into that array, which have alignment requirements if you want to align load, which is a bit faster, not that important. And then what is kind of nice, the equality operator is overloaded, so we can do just a simple comparison, and that will do element-wise comparison under the hood of nth elements. And that will return a SIMD mask, which is kind of like a bit mask for purposes of this talk. If it's 0, it's undefined, so we have to do any of, which looks like just an algorithm. And if you have a match, we can just find the first set in that match, or the last set. We're just assuming that one value will be in the enum, as I pointed out before, and we grab it from the values. So I think the implementation is quite simple, easy to follow. And how the assembly looks for that. So there's more interesting thing here. So first one is the broadcast. You can see that's one cycle to broadcast the input value into the registers, into the vector. And then we have the comparison, and all these instructions we start with v, they vectorize. You can see that the latency of the second one is 8, and it has the load. And it's 8 because the 5 cycles is taken by the load itself from the memory. And because it's address taking, and 3 cycles is taken for the comparison. Then we do the move mask, which is just a single instruction, and then we find the element which is in that register afterwards, the 1 bit, which is the least significant bit. Maybe that's a bit confusing if you're not familiar with that, but the idea and the importance of that is the fact that we have no branching, right? There's no if-else, there's no tests, there's no comparisons. Because we do, well, there's a comparison. We do all of them at once and return the one which actually matches. So I hope that makes sense. But can we do actually better if you have the case which is kind of more complex? You can imagine that we have an enum which has part of it kind of close to each other, really dense, and then there's like this odd, values somewhere else. So that works pretty well. That doesn't work pretty well with SIMD, right? Because if there's a lot of elements here, we'd have to go through in the loop, which may work efficiently or not, depending on a lot of things. But one thing which you can do is apply a switch case. Everyone familiar with switch case? No one is sleeping it? Less and less people. So let's get into that a bit more. So if you take a look into the GCC, there will be 1 million line, probably, file which will have all the implementation for the lowering strategies of the switch case in GCC. And what can GCC do is actually very interesting, because Clang can't do all of that as well. So can do the GCC can do the, for example, bit set. When we have the case like that, and you can see here what we have ASCII 0, 3, and A, that will be just converted to a value which we can do bit test on and return whether we found it or not afterwards. So that will be just a single one cycle instruction to get it. Clang doesn't do that very well. But what is maybe more familiar is that when we have cases which are really dense, the switch case can generate a jump table under the hood. And all of that is happening into the cluster. So GCC, like the compiler, is looking into, can I do the bit test for that part, or can I do the jump table in that part, and stuff like that. So that's happening per cluster. And maybe numbers which not everyone is familiar with is, how spread the values have to be in order to generate the jump table. So in GCC, that actually, and Clang is the same. It depends on whether we compile with OS or whether we compile with O3. If you compile with O for the size, they have to be not further than 2 away. Like they have to be as close. Because we want them to be dense because we care about the binary size. Otherwise, if you compile with O3, it's 8 is the magic number here. And also we care about not producing jump tables for the small number of cases, so 5 is the number here, where we will prune after that. So finally, what switch will do in GCC and Clang is the decision tree, which is the if-else kind of approach one by one, like we've been doing with the if-else. But what is interesting is that, because that's just labels, there's no guarantees that the 42 here will be handled first. If you want 42, like an if, the order is important. Here, if you want the order to be important, we have to put this built-in expect with probability that the 42 is the most likely case. So if you care about the performance and you know that this guy will be the most likely to be found, that's how you can do that. You can also apply PGO, but you may overfit afterwards. So that's about switch. Can we actually generate a switch out of compile time values? That's a question which is interesting to take a look at. And we actually can. So in this particular example, we'll do we'll leverage deducing this, which is C++23 feature. If you're not familiar, that's the this author, which means that we propagate this is not implicit, it's explicit. And that allows us to, do recursive lambdas without passing ourselves to a lambda afterwards. So how does it work? Usually it's hard to generate the switch because, we cannot just fold over the TSS. But if you look into that more deeply, we can actually go to the default and get the next case recursively being called with the next value. Right? So in that case, we'll go to the switch. If that's the case which we're interested in, we return. If it's not, we call the switch again recursively with the next value. Make sense? And it's worth pointing out that this optimization depends on the compiler, right? So GCC and Clang can really well optimize the nested switch, but not all compilers can handle that properly. So for the switch case, let's take a look into how that will be implemented, how that will compile. So if you look into the assembly, it's kind of interesting because you can see in the beginning that it subtracts 200 from the input register, and that's calling convention for GCC. That's the lookup table for the, OK, created. Then we verify how many elements are there. That will be this comparison. And then we load the jump table, which is on line 7. And after that, we will go and do the comparison for the leftover cluster, right, which is the 403 value. So that's why switch is very powerful when you have things spread around and you can leverage the information for a few underlying clusters. But it's also important, you can see this unknown value being 0. And that's important for performance because you can see the ZOR EXX on line 10, it actually costs us nothing. It's like 0 cycles if it comes to the latency. So that's also important. And on the bottom, we also have the C move, which is the conditional move, which doesn't do the branching, but has to calculate both cases. And it's beneficial if the data is unknown and we cannot predict it. So in C++, potentially we'll be able to do stuff like that natively. There is a proposal which is called code injection with token sequences, which will allow stuff like that, but that won't be before 29. There's also code recons, which kind of tries to apply similar concepts. And without going into details, the idea is that we have these meta functions, and syntax will likely change to generate those cases at compile time. So that'll be interesting at some point, but we don't have it at the moment. What we can do the switch case nested version instead. But all these cases were kind of interested, but not maybe there was not that much magic in it, right? Can we do better? Well, we can actually do even better when we leverage the compile time information of the cases we have, because we didn't really so far. So that's where the perfect hashing and the rest of the talk will go about. So hashing is an interesting, space. Everyone is familiar probably with the universal hashing. That's part of the, our maps, STD map, STD unordered map. And the idea is here that we have the hashing and it can have collisions. And you have to sort them out. How you sort them out depends whether you have open addressing, like unordered map, or closed addressing, like STD map. And boot unordered map, which implementing open addressing, is boot unordered flat map, is very fast, so you might be interested to see that. If you have time, we'll take a look into that. So perfect hashing, on the other hand, doesn't have any collisions. It still may have empty buckets in the lookup table when we map the values, but there will be no collisions. So the idea is here we know keys in advance, and we find the hash some way, or the mechanism behind it, that we won't have any collisions. So obviously that has the performance benefit that we don't have to, do the collision resolving afterwards. And finally, minimal perfect hashing, which is the case which is the hardest to find, but we will have example of that, is that we don't have any free spots in the lookup table. So meaning the mapping is kind of just in a different order. It's very difficult to find it, but it's possible. And there's a lot of research in that area. If you can take a look yourselves, I just pointed a few papers. There's a lot of them. Most of them are focusing though on cases where we have like more than 1 million elements, and they're focusing on lowering the number of bits required to represent the keys. Not much about the lookup time. So let's try to leverage hardware accelerated perfect hashing. We're on x86, well, let's leverage that. So let's look at those numbers. We have the keys which we want to hash to get the performance. If you represent them differently, we can use the binary representation for them. And after that, the idea is that we'll find the significant bits which uniquely identify all the numbers. So you can see here that there are 4 bits. You can check it yourself if you like, but I guarantee you that that's the case, that those 4 bits which are highlighted here can uniquely identify all those numbers. So if you take a look into those 4 bits, we can say which number that is. And having that mask, we can then do the perfect hashing, and the lookup table will be of the power of 2 to the number of bits in that mask. And we'll take a look into the implementation in a second. But that's the idea here. And why we care about this mask so much? Because on x86, there's this instruction which is called BXT, and it's from BMI2, which is the bitmap extract manipulation feature, so that it costs 3 cycles, it has 1 throughput, and given the value, and that's the input value like our enum, and the mask which we compute at the compile time, it can, in 3 cycles, mask it, and compress it to the, to the right side in that case. And why that's important? Because then we can just index into the lookup table. Because hashing is all about compressing, right? We have large space of numbers, and we want to compress them into smaller space. So does it make sense? Okay. And if you're interested in the instructions, you can read the manual as well. So how we go about it? So in order to do that, we have to implement the lookup table. And that's kind of simple. If you follow the JSON tags, we can do that at compile time with the immediately invoked lambda. We have an array of 2 to the power of the number of bits in the mask. And then for each element which the PXT finds for that mask, we put the enumeration and the name. So that will be our lookup table will be filled with enumeration and name, and there will be some empty spots in that as well, which depending on the pxt instruction. So this pxt has to be implemented at compile time, at runtime, as well as the mask. And what is the lookup? And the lookup is very simple. We just do pxt of the value and the mask, and we just index into the array. That will return us the key, potential key, and potential mapping for that key. But we still have to compare it because our perfect hashing is only for the keys which we know up front, and outside values may also have hash which will collide. So in that case, we have to compare it, but it's just always guaranteed to be one comparison. So there's a lot of challenges with that implementation because we have to do that at compile time. So if you take a look into this mask const eval implementation, how we can go about it? We have the bit set with all the bits set to 1. And then we iterate over that mask. We flip the bit, meaning we set it to 0, and check whether all values are still unique with that mask. If they are, then great. Then this bit is required, not great. Otherwise, we flip the bit back and we iterate again. So that's a simplified version because this problem is NP hard. So that works, and you have to do it at the compile time, so it takes a lot of time. Making it fast at compile time, it's kind of challenging because we cannot do parallel execution at compile time, but it's possible. And if you're interested, I have benchmarks for the compilation times as well. So let's take a look into the assembly out of it, because that's maybe where the interesting part is. So the pxt on Clang actually often is changed into instructions which are more efficient in that case, and has just 1 cycle, and pxt has 3 cycles. But you can see what is happening here. We do the pxt, or in that case end, and then we do the comparison for that key with the value which we got. We have 2 loads. Out of that, we do the cmove and we get the value, right? So it's always the same. It doesn't matter what's the input, or like the keys on the bottom doesn't matter. That the keys and values only will change the mask, the number in the on the line 3. So it's a constant lookup time, actually constant lookup time. So hopefully that's exciting because that's really fast. But can we actually do better? If we can guarantee that all the values are from the predefined set which we have already, meaning like we can guarantee that the value will be red, green, or blue in that case. And sometimes that's the case for enums because, if you don't allow static casting or anything like that from the kind of random values, you can potentially guarantee that. We can implement this unsafe version and overload it if we know. And that will assume that the value will be contained in the enumerators which we have provided, and we don't have to do the comparison at all. So basically, if you take a look into the assembly output, that's the assembly for this lookup. So we do an end, which is 1 cycle out for the input, and then we just load the result. And notice here that the lookup table is minimal. It just has 3 elements. It doesn't have any keys because we don't have to compare with it. So can we do better? There's one solution which you can do better as well. But what is interesting out of that very well scale into different inputs. So the only thing which will change out of this assembly is the mask, the number 3 in that case. That will be just a different number, and it might be a pxt instruction. So hopefully that's exciting because that's really fast. But what if you don't have the BMI, or you are actually anyone AMD fans? Not a lot. So if you take a look into the UOPS website, you will find that there is a pxt instruction cost on basically everywhere besides Zen 2 to be 3 cycles. Otherwise, it's much more expensive because just happened. But if you don't have x86 and you're interested in still that solution, it's possible to do that with different instructions. So this pxt, which is 3 cycles on when you have BMI2, might be, in many cases, not all cases, change into a few other instructions like end, imul, and shift right, and end. And if you're interested into that approach, look, actually a bit of story time, because that's interesting and actually was funny to me. So when I was implementing that and sharing that, Luke, which is working for Intel, reached out to me saying, oh, you know that your library, like it's really fast, but it requires this specific Intel instruction. And I was, well, you work at Intel. What's the problem, right? Well, unfortunately, he is working on the power management, embedded stuff, and they don't have that instruction. So he had to find a different solution. I just find it interesting because he's working for Intel. But overall, there's no silver bullet. If it comes to enum to string and any solution which you care about the performance, you have to do your work, you have to know your hardware, you have to know your data, and you have to likely to do a lot of overloads or ifcon's expert under the hood in order to support and make it as fast as possible. And that's what this enum to string, which is shown here, is doing. But let's take a look into the benchmarks. And if you want to run them, there's a notebook provided with way more data than you actually want to take a look likely. But that's visible. So how does it scale for up to 16 elements? You can see that if else and switch case scales up to 5, more or less 6, because then the branch prediction, missed branch prediction is actually very costful. If you take a look into frozen, it's kind of okay, but what is interesting is boost another flat map. It's very well performing in that case. And if you have time, we'll take a look into that why. Another map and map, not as much. But the flat line is our hardware accelerated perfect hashing. So if you care about performance, here you go. And how does it scale? Oh, damn it. Quick recap. I hope you are following. So, it's like enums are usually small. I don't know, up to 100. 16 was the interesting case for me, but up to 100, it scales exactly kind of very similarly. You can see the flat line on the bottom. It's like significantly faster, order of magnitude faster than anything else, which you can explore and leverage afterwards. So hopefully that's exciting. We still have time to do the string to enum, which is even more exciting because everyone has strings in the code and want to translate them to integers or like IDs. And again, there's a lot of solutions, and we'll get to the bottom one. We'll go a bit quicker this time. But let's take a look into how you can do that with the reflection. It's very similar. That's the power of the reflection itself, right? You can just do this enumerators and just go and compare the strings. But we'll compare the strings here, so that'll be really slow, not worth anyone's time. Switch case is an interesting as well, because we can do the hashing or just the bitcast in cases where we have up to like, let's say 8 elements. We can cast the value to be like uint64 for 8 characters. Or we can do the hash. We can have a hash at compile time, hash at runtime, compare them, and do the switch, because switch doesn't work on strings, right? So that's one option. We can do this try thing, which is interesting. And if you're using Boost Beast, that's how they're doing that. And the idea is here that we find the interesting characters out of the input and switch on those. And if they're unique, we're good to go. If you're not unique, we find another characters or the size or something like that to go a bit further. Make sense? So there's a lot of comparisons here, but you get quickly to the solutions which you want, and you don't have to compare everything. So that's interesting, and you can generate that compile time, right? With the reflection, with the info objects, you can do stuff like that very easily. The most common solution will be the unordered map, right? If you know the values, you just do the static. But what is interesting, if you're not familiar with Frozen and you care about the performance to a degree, you can do the following. Instead of unordered map, static const, because unordered map can be const expert, you can just do const expert frozen, and you have to put the size as the third parameter, but that's it. That's the only change you have to do. And if you know the values up front, you can leverage perfect hashing under the hood, which will improve your performance and lower the binary size. And the gperf is one of the most, and kind of old, but a very interesting tool used by GCC for parsing C++, used by Chrome. Anyone familiar with gperf? A few hands. You can read the paper. It's very interesting how it's been done. It only supports string-like keys, but it's very, very performant. It requires code generation though, so you cannot leverage, your C++. You have to generate the code out of it. But if you want performance, we have to do more, right? We care about that so much that we'll show how to convert the string to an type, like an int, in order to do the things that we've done before. Because if we have the ints, it's like an enum, and we can leverage the solutions which you had before. And this way you can implement, optimized string, right? With the following solutions. So like if you have int under the hood, you can have 4 characters. Int64 will be 8 characters. SIMD, you can leverage to have up to 64 characters. And this way you can do very efficient operations on the vector, on the string. But how we do that? So if you know the size at compile time, which is here because we passed the list row, that will be optimized away by memcopy. You can, if you're interested into that, how to start the lifetime, you can, Robert is here, you can listen to him. He has a great talk about how to actually do it properly. But we can do memcopy out of it, and that will be optimized to the cast if you have the size matching the type that you want. But if you pass the string view and we do this str size, that will be slow. That all our perfect hashing will be totally useless because this memcopy will just take forever. So what we can do about it? We can do potentially unsafe, but mainly valid. Idea is that we do memcopy more when we, like size of t, in that case, like uint64, let's say. And then we leverage this instruction on Intel to zero out the bits which we are not interested in. Why that might be potentially unsafe? Because we can be on the page boundary, and if we reach that part where we shouldn't, we can be in troubles. But we can have a workaround, which is actually taken from blipc. If you look into the memcopy.h, that's exactly what they're doing, just in the C style. We verify whether we're close to the page boundary. And if we are, we go the slow path. Otherwise, we go the fast path. And that can be proven that that's very low frequency where we will be close to the page boundary, and that's it. That's how we can leverage the two from the int from the string view to an int. Make sense? Important to have that. You can assume it depends whether you have huge pages or not as well. Not maybe that interesting, but used by Glipsy, so kind of approved. Okay, so if you have that, everything else is kind of trivial. You know, like my teacher used to say, the other way is always trivial. So that's the code for the perfect hardware accelerated perfect hashing from before, and the only difference here is that we, do this string view to a uint or whatever SIMD type you have, and the rest is the same. And just to look at the assembly to show that the previous cases weren't just a fluke, and that actually works, is that and that's the lookup for the string to enum. At first we do this pzhi, which we do the cast, we grab the bits which are interested in. Then we do pxt, the mask is 17, and rest is as before, just lookup, comparison, because that's assuming that we may not find the key, and grab the value. And you can see these numbers on the bottom that they just represent the strings. But just to do the final thing, we can also do even better. And we'll do the minimal perfect hashing, the minimal hash table as you can get. For that, we have to have specific, because that's harder to find. All this perfect hashing may fail. We'll have the enum here, and the values on the right side, they might be different, but for simplicity, we'll do the following. So if you have enum like that, and you will be surprised how many enums can be actually found to be minimal perfect hashed this way. What we do, we get this value, we try to find the magic number, we shift it, and we'll get something which will do the perfect hashing for us, meaning that we'll do the minimal values. So this value times magic, sorry, I was going about, so the shift, which is important, is the number of bits, the number of bits which are required is we have to know number of bits which are required to represent all the values. In that case, the 4 is the max value, so we need 3 bits to do that. Then we subtract, we go for the uint32 for simplicity. We subtract these 3 bits, that will be the shift will be 29. And then on the bottom, we'll look for the magic number, which when we get these keys as strings, multiplied by that value and shifted will give us the perfect minimal hashing, because 14023 is exactly how many values we have in that And then, even better, we can do the lookup table in the register. So if you have those values, this indexing might be changed into the binary, and this binary that's equivalent might be represented as one single value shifted by nth multiplied by, in that case, 3, which is the number of bits required to represent the max value, and must with the, these 3 bits which we get the value out of, and that's, semantically equivalent to those indexing. And then the whole lookup, and this whole lookup table here looks as the following. We have the lookup table, which is the value. It's not a lookup table, it's a value shifted by this bit mixing and with the mask. So what we have the shift up front, because we know it's 29 bits, because we need 3 bits to represent the values. We know the mask, we don't know the magic and the lookup. And to not much time, but so these are the values which we have to we discussed. Notice here it's mag attempts is how many attempts we will do to find the magic in a second. And then the lookup looks as the following. We just get the value and do a few multiplication, shifts, and masks. But it's super cool that C++20 allows us to actually compile that. So notice we'll use compile time pseudo-random number generation at compile time. All of that is const-deval. And we'll populate the lookup table. And then we try to find whether this lookup table gives us the enumeration which we want. And if it's not, we go further and try again and again, up to millions sometimes times. You may wonder, that compiles minutes. No, it compiles very quickly. It's the power of magic of const_expr if you do it right. So you can check it on Godbolt. I will provide the links. It gives the results instantly, very quickly. So that's the lookup. That's the magic behind that, and how the assembly looks for that. So the first thing is the same, right? We do cast, we get the bits which we want, and then notice here that we don't have a lookup table at all. There's no caching involved. We don't have to log into anything because the lookup table is actually stored in the register. So the first thing, we multiply by this magic number, then we shift it by the bits which we have to get the values which we want, get the lookup table on line 6, which is all the values, and I put it in a binary here. That's not the case in the Godbolt, but I just made it for simplicity. And we just shift right and mask, and we get the values out of it. So that's pretty cool. If you constrained, if you don't have cache or anything like that, you can leverage techniques like that, and you can count the number of cycles required to do the lookup, which will be 4, 7 plus 6 in that case, and the return. So out of string to get the actual value. And quickly, how that looks for the benchmarks. As kind of pointed out before, if you look into any other solution, this is just flat. It's constant lookup. And constant lookup, like 01, but it's 01 in an assembly kind of level, meaning always the same, just values change. There's no other magic. Like with if-else, it depends on your state of the branch prediction and stuff like that, so you get much lower lookups. But what is interesting, if you know the gperf is here as well, and the gperf is also slower. So if you want to gain some performance, you can leverage that technique. And if you're interested in the perfect hashing benchmarks, I did kind of extensive research into that. And lookup is just one part of it. You have cache utilization, you have binary size, compilation times, and many other counters which you can leverage and see. And you can run the notebook yourself on your hardware and see how that's goes. So just to sum up, it was a long talk. So what is the interesting part of it? Compile time reflection will impact how we write the code, no doubt about it. When we have the compile time information and low-level control, like C++, we can gain performance. And there's no silver bullet to the performance, just trades-off. And always measure, but always measure in your use case, because there's no silver bullet, as I pointed out before. And with that, thank you.